Good day and welcome to lesson 2. In lesson 2, we'll be looking at friction and wears. My name is Engineer Sonny Oboji, and I'll be taking us through some topical issues as it relates to friction and wears. To begin with, friction can be defined as the force that opposes the motion of a solid object over another. When you have a solid object trying to move over another one, the resistance that occurs, that resisting force that ensures that the movement is not a free pass, is called friction. Friction and normal force are directly proportional to the contacting surfaces, and it doesn't depend on the hardness of the surfaces. You could have surfaces that are equally hard. You could have surfaces that have different levels of hardness, but it's been proven that the frictional force that is generated between the surfaces is a function of the area, the amount of surfaces that are actually in contact, and not really the hardness of both surfaces or any of the surfaces. Now, there are about 4 different types of friction. There could be other, but the main types of friction, which depend on the types of motion, will include 1, static friction. In static friction, there's no motion, and one surface basically rests on the other one. There's no motion involved. Then we have sliding friction. In sliding friction, there's a sliding motion. One of the bodies attempts to slide over the other one, and then there's this frictional force or resistance. So that's sliding friction. The third kind of friction is rolling friction, which comes to play when you have a rolling motion. And finally, we have the fluid friction. I will attempt to explain in some form of details each of these types of friction. But for comprehensive details, you might need to refer to the notes that will be posted on the website. The notes are more detailed. Now, static friction is defined as the frictional force that acts between surfaces when they are at rest with respect to each other. The magnitude of this static force is in the opposite direction when a small amount of force is applied. But when the force increases at some point, maximum static friction could be reached. Examples of static friction. For instance, if you are skiing against the snow on a snowy day, that's some static friction. Then normally when you rub both palms together, some heat is generated. That's another good example of static friction. And for a table that is resting, table lamp, for instance, that is resting on the table, that's a very good example of static friction. The second type of friction, sliding friction. Sliding friction can best be described as the resistance that is created between two objects when they attempt to slide against each other. One could be stationary, the other one is trying to slide over it. The resistance, the frictional force that is generated is called sliding friction because of the sliding motion that is involved. And the examples of sliding friction include sliding of a block, for instance, across the floor, or the solid base of a machine or an equipment across the floor as you are trying to slide it. That resistance is called sliding friction. Or you may have a case where two cards are made to slide against each other in a deck of cards. What you experience there is called sliding friction. The third kind of friction, rolling friction. Rolling friction is defined as the force that resists motion of a ball or a wheel and is the weakest type of friction. Normally, there's a surface, which could be a ball, normally cylindrical surfaces. As it attempts to roll across another surface, the friction that is generated is called rolling friction. 2 examples to mention: rolling of a drum on the floor. As you attempt to roll the drum on the floor, the frictional force that is generated there is called rolling friction. And then when you have wheels of a wheelbarrow, wheels of your automated trucks, wheels of your pallet trucks, or any other kind of trucks that are used in the industry, as they roll on the floor, it generates rolling friction. Then we have fluid friction. Fluid friction can be defined as the friction that exists between layers of the fluid when they are flowing relative to one another. Now, if you look at a cut-through profile of any fluid, you will see that there are different layers. There's the boundary layer, then there are there's the layer that is next to the boundary layer and the innermost layer, so on and so forth. So what happens when a fluid flows is that different layers tend to move relative to the next layer, the adjoining layer, and the friction that is generated there is called fluid friction. Examples include the flow of inks in pens, or any form of when any form of liquid flows in capillary tubes. That's fluid friction. And then, of course, friction that you encounter when you attempt to swim. Now, having looked at friction, the next thing we want to look at is wear. The issue of wear is a very serious issue in engineering because we encounter it in everyday life. It leads to deterioration of materials and significant losses. And so we give it some serious attention. Wear is the gradual removal or deformation of materials at the solid surfaces. Normally, when you have a piece of metal or any solid, it wears off from the surface and it eats deeper and deeper into the thickness of the material. But it begins at the surface because at the surface that the interaction that leads to wear actually takes place. Now, wear of metals will occur by plastic displacement of surface or near surface material and by detachment of particles that form the wear debris. Now, as wear continues, it files out the surface into very, very tiny, fine particles, which almost, depending on the strength of the material and the nature of the material, could be powdery in nature or it could be gritty, and we call those particles the wear debris. The factors that affect the wear rate include the type of loading, and here we may be looking at impact loading, static loading, or dynamic loading. So we may have any of these three cases of loading. It can actually affect the rate of wear. Then another factor is the type of motion. Like we saw earlier, it could be sliding motion, it could be rolling motion. Then we have temperature. The temperature of the material could also affect the rate of wear. The level of lubrication. Naturally, where there is lubrication, or adequate lubrication, you see that the wear rate is reduced. And where there's no adequate lubrication, the reverse is the case. In particular, by the process of deposition and wearing out of the boundary lubrication layer. So as the lubrication is taking off, there's metal-to-metal or material contact, direct contact between the contacting surfaces, and wear ensues. Now I want to look at the types and the causes of wear. The types and in particular what causes wear. And we have quite a number of them, but we want to first consider friction. Frictional wear is a kind of wear, and frictional wear happens because of the energy that is generated or created by the continual motion between a pair of adjoining surfaces. As the surfaces continue to rub against one another or move relative to one another, energy is created by this motion, and it results in some form of wear. And it can typically manifest by linear grooves, the formation of linear grooves by the countering contact. So all of a sudden you begin to discover that there are grooves that are formed on the profile of the surfaces that are in contact. Although it is one of the least damaging causes of wear, frictional wear can cause fatal damages if left unchecked over a long period of time. The second type of wear is heat-induced wear. And here, we know that high temperatures result in the softening of metal parts, which actually can cause wear and tear, as also a noticeable degradation of the properties of the material trigger other forms of wear like erosion and abrasion. Erosion and abrasion are two kinds of wear that are related to heat. When the temperature of the material goes up, they become susceptible to this kind of wear, erosion and abrasion. Now, taking a particular look at abrasive wear will occurs when any moving surface contacts another surface. It begins to become a major issue when a larger and more solid material makes contact with a softer one. You see that the more solid material and the stronger material tends to wear out or to cause serious abrasion in the softer one. The softer one actually pays the price. Abrasion happens with two similarly hard surfaces also. So it's not a case of one being stronger. Even when they are of equal strength, then there's almost a commensurate level of abrasion happening on both surfaces. The wear is referred to as two-body wear if it's only two surfaces involved and there's no third surface or particle in between them. If just the two surfaces that are rubbing each other and producing the wear, we say it's a two-body wear. If the wear is caused, however, by a hard particle, for instance, a grit trapped in between the rubbing surfaces, then it is called three-body wear. So we have two-body wear, we have three-body wear. The particle may be either free or partially embedded into one of the mating materials. Now, whether it is free or embedded in any of the materials, it has an effect of wearing out or cutting part of the contacting surface, especially if the particle is stronger than the surface that is making contact with, and before you know, wear takes place. Then the third cause of wear, and the third kind of wear we want to look at is erosive wear. Erosive wear occurs when smaller parts are impressed on a larger surface and progressively remove small fragments of the bigger surface material just because of continuous momentum effect. Now, especially if you are looking at a situation where a heavy object makes contact with a lighter object and at increased speed, then the momentum that is generated, which is actually a product of mass and velocity, is higher, and it can cause the erosion of the smaller part with time. Another cause of wear is cavitation. Cavitation is a very, very serious phenomenon when you are dealing with pumps, especially the impellers, the internal casing, and the internal components of pumps. Now, cavitation can be defined as the rapid formation and eventual collapse of tiny pockets of air or vapor in flowing liquids in locations with extremely low pressure. You see, for us, your flow is initiated by the pumping action from the source as it enters into some low pressure areas within the pump. The bubbles that were formed or that were carried along in the fluid, they burst in the low pressure areas, and then the rapid bursting of these air vapor or bubbles tend to cause pitting or cavities to be formed, and that's what we call cavitation. It is the usual cause of structural damage on machinery with pumps and propellers. It's a very, very serious problem that needs to be given attention if our pumps and other things within the flow system are to last and serve us well. Then we have impact wear. Impact wear happens when a solid surface consistently impacts on another solid surface. This results in material's progressive degradation. First there's the formation of a profile, which is a representation of the shape of the contacting surfaces as a result of the impact. With progressive impact, you see that it cuts the profile on the other surface that may not be as strong as the impacting force. This happens when, even if the surfaces involved are made to withstand this type of contact, it's something that happens over time. And then we have the corrosive wear, or wear as a result of corrosion. Corrosive wear could be very dangerous, and it's usually caused by the degradation of the surface of the material because of an adverse reaction to something that is foreign in its setting. This includes leaking water or chemicals. The water and the chemicals, as they drop on your metallic surface, there's a reaction that ensued, and because of that, there's a damage to the surface of the material. In most cases is metallic. There's a some damage is caused, and we see that surface wearing away and getting removed. Having looked at the different types of wear, and it is important we consider how to prevent wear, because it's a very big problem in engineering and especially in industrial settings. How do we prevent wear from occurring, or how do we minimize the wear rate so that we can ensure longevity of our equipment? In most industries, wear caused by abrasion could be a major and a complex problem. I must stress again. Other issues that could cause wear include impact, scuffing, erosion, fretting, rolling, and galling. Now, at the basic level, our tools could be equipped with diamond composites or inserts like carbide, tungsten, cobalt, could be used to prolong the lifespan of the machinery. What they do is that where you have these inserts or these coatings, they harden the surface and make it less susceptible to wear, even on impact or whatever. Alternatively, also, as a way of preventing wear, many industries today integrate wear technology into their operations. And wear technology is all about introducing and pushing the most fitting and the groundbreaking concepts of material science into heavy industrial processing and bulk material handling facilities. It has as its main goal, to minimize or reduce downtime of the machinery and equipment in facilities and decrease ownership cost. It also increases safety, profitability, functionality, and performance of the facilities. We're talking about technology that focuses on wear, the nature of the wear that is anticipated when that machine, when that equipment will be used. And then it tries to eliminate the conditions that will need to come together to cause wear to be able to take place. So by design, you eliminate those things and make the machines, the equipment hardened enough so that they will be less prone to wear. So by way of summary, under this lesson, we have looked at what friction is. We have looked at the types of friction, and we identify 4 types of friction: static friction, sliding friction, rolling friction, and fluid friction. Now, having looked at the types, we also went further to analyze what wear is, identify wears, and the factors that affect the wear rate. We looked at factors like the type of loading, which could be impact, static, dynamic. We looked at the type of motion, it could be sliding or rolling. We looked at factors like temperature, lubrication, and other factors that could affect the wear rate. Then we looked at types of wear and what causes each particular type of wear. Here we looked at frictional wear as a result of heat, erosive wear, cavitation, impact wear, and corrosion. And lastly, we looked at how to prevent wear. Either you are designing and using inserts that are strong enough to withstand wear as part of your machinery, your tools, your equipment, or you engage in wear technology, which focuses on design of materials and use of materials that are less susceptible to wear. Thank you very much. That's the end of this lecture.